All right, let's get right into it. Today, we're putting on our detective hats for a really cool chemical mystery, the fading violet experiment. So, picture this. You have this incredibly vibrant purple solution called crystal violet. You mix it with a little sodium hydroxide and it just vanishes. Poof! The color just fades away into nothing. Our mission today is to figure out exactly how, and more importantly, how fast this amazing vanishing act actually happens. Okay, so every good detective story starts with an investigation, right? Our first step is all about the setup. We need to watch this reaction unfold in real time. And for that, we need a special gadget. Our number one tool is this thing called a spectrophotometer. Now, how it works is actually pretty simple. The deeper the color, the more light it soaks up. This machine shoots a tiny beam of light through our violet solution and measures how much of that light gets blocked. So, as the color fades, the amount of light it absorbs drops. This gives us a perfect, live feed of the reaction's progress. It's like watching the whole thing on a monitor. Here's our game plan, broken down into 4 simple steps. First, we get our solutions ready. Second, we calibrate our spectrophotometer to make sure it's accurate. Third, the main event. We mix our chemicals and hit record to start measuring. But honestly, the most critical step is number 4. We do the whole thing all over again, but this time in an ice bath. And you'll see in a bit why that cold trial is the key piece of evidence we're looking for. You know, just following steps is one thing, but a good scientist and a good detective needs to know the why behind them. We use a blank, which is just water, to tell the machine, hey, ignore the glass vial, just pay attention to what's inside. Then we find the exact wavelength of light that the violet color absorbs the most, around 590 nanometers, to get the strongest, clearest signal possible. And that cold trial? Well, that's our secret weapon. It's how we're going to figure out the energy of this reaction. All right, phase 1 is complete. We've gathered all our surveillance data. Now it's time to head back to the lab for phase 2, the analysis. We're going to decode these numbers and figure out this reaction's unique speed profile. And that brings us to the biggest question of our investigation. Is this reaction 0, first, or second order? Now, I know those terms sound super technical, but don't worry. They're basically just labels that describe how the reaction speed changes as the crystal violet gets used up. And the answer is hiding right there in the data we just collected. So, how do we find it? Well, we basically put our data through 3 different tests. We're going to plot it in 3 different ways, and we're looking for one simple thing. A straight line. Whichever one of these 3 plots gives us a perfect straight line will tell us everything we need to know. It's a process of elimination, and only one can be the winner. And there it is, the moment of truth. When we plot the natural log of our absorbance data against time, we get a beautiful, straight, downward sloping line. The data has spoken. This is, without a doubt, a first-order reaction. And what that really means is simple. The more purple color there is, the faster it fades. As the color disappears, the reaction slows down in a very predictable way. Now, because we found that straight line, we can figure out something really important called the rate constant, which we just call K. And get this, the slope of that line is the rate constant. Think of K as the reaction's own personal speed limit. Every reaction has one, and it tells us precisely how fast it's going to go at a certain temperature. It's a unique fingerprint for the reaction's speed. You know, any good detective always double-checks their work, and we can do that by looking at something called the half-life. That's just the time it takes for half of the purple color to disappear. We can actually just look at our graph and get a pretty good estimate. But because we know this is a first-order reaction, we can also calculate it using a simple formula with that K value we just found. And when the number from the graph and the number from the formula match up, we know our conclusion is rock solid. So we figured out the how fast. We know its speed limit, but that's not the whole story. Now we dig deeper. What's the motive? What's the energy that's really driving this whole thing? Hey, remember that experiment we ran in the ice bath? This is its moment to shine. Just as you'd expect, when things got cold, the purple faded way more slowly. But that slowdown isn't just a fun fact. It's the final, crucial clue we need to solve the entire case. And that clue leads us to something called activation energy. The easiest way to think about it is like an energy hurdle. For the 2 chemicals to react, their molecules have to bump into each other. But it's not enough to just tap each other. They have to collide with enough force, enough energy to get over this hurdle. That minimum energy they need is the activation energy. And this is where it all comes together beautifully. We have two different speed limits, or K values, one from the room temperature experiment and one from the cold one. By plugging those two speed limits and their two temperatures into a special tool called the Arrhenius equation, we can calculate the exact height of that energy hurdle. We can put a precise number on it. And with that, after all our investigation, our data collection, our analysis, we can finally say it, case closed. Let's wrap up everything our detective work uncovered. So here it is, the final rap sheet on our fading violet. We now know its complete profile. We determined its behavior as first order. We found its unique speed limit, K, at two different temperatures. We calculated its half-life and confirmed it. And finally, we measured the exact energy hurdle it needs to clear to even happen. We've cracked this thing from top to bottom. So we solved the mystery. We know how fast it goes, and we know why it goes that fast. But solving one mystery always opens the door to a new one, doesn't it? The next question is, now that we understand it so completely, how could we control it? How could we make it go faster or slower, or even stop it in its tracks? And that's where this kind of science gets really, really powerful.